Today we will see bending of a beam. Here on the board, this is the beam. The cross section area of this beam is a rectangular type. If you see that the length of this beam, and this is the cross section area, the length of this beam is, as compared to this cross sectional area, is very large. This type of rod is called the beam. This type of beam, it is of wood, maybe of iron, cement. This type of figure is a beam. Now this beam is clamped at the fixed surface, and the free end to the free end a load is applied. Due to the application of this load, this beam bends and an extension produces at the upper surface. Due to the extension, the upper surface becomes convex. At the same time, the lower surface of this beam becomes it is being contracted and the surface becomes the concave. Due to this extension and contraction, there is this beam bends. But due to this load, what happens? The bending, this type of operation or this type of is called the bending moment. Now we want to calculate the changes here in this bending. For that, we consider this type of figure. Suppose we consider a small cross sectional area. यामध्ये काय करू आपण, छोटासा एक क्रॉस सेक्शनल एरिया यामध्ये आपण कन्सिडर करू. सपोज तो क्रॉस सेक्शनल एरिया काय आहे, सपोज ही बीम अशी बेंड झाली, तर सपोज दिस इज द सरफेस EF. EF सरफेस वरती काही चेंज होत नसतो. याची लेंथ वाढतही नाही आणि कमी होत नाही. द लेंथ ऑफ दिस सरफेस, दिस इनरमोस्ट सरफेस, इट्स लेंथ डज नॉट चेंज, but the length of this lower surface and this upper surface get changed. This upper surface gets elongated and this lower surface gets contracted. Now this change we want to calculate. For this, suppose this is a part of a circle and this we draw like this. This is the R. Now we will calculate this. Suppose here this A dash and here it is B dash. The length of this AB and AB dash. Here the length of AB is less than this length. This due to this load, there is a elongation takes place, and the length of this A dash B dash is more than this AB dash. Then we will consider it like this. The radius here it is x1, it is x1 and x2, here it is y1 and y2. Now let x1 y1 is a small segment of a neutral axis. Let x1 y1 is a small segment of neutral surface EF, neutral surface EF. This EF is the neutral surface, means there is no change in the length of this layer EF due to this load, due to the load application of this load. Now, thus OX1 equals to OY1 equals to OY1 equals to R. This is the original length of this beam. Before applying this load लावण्याच्या अगोदर त्याची लेंथ ह्या EF ची लेंथ आणि अगोदरची वापरलेली असलेली लेंथ हे कशी असणार आहे, सारखीच आहे ना. therefore the x2 y2 since x2 y2 is longer than x1 y1 is longer than x1 y1. x1 y1 पेक्षा x2 y2 हा काय लॉंगर आहे. x2 y2 here it is y2, x1 x2 y1 y2. x2 y2 is longer than x1 x2, and this change we want to find. Then on bending, therefore here this x2 y2 minus x1 y1, what happens? This change, when this change happens, when this load is applied to the beam, if it is equals to x, suppose it is equals to x, that is the extension of x1 y1 on bending, equals to extension of x1 y1 on bending. Okay, then we have x2 y2 x2 y2 then we have x1 y1 upon r equals to theta upon r equals to theta. This is the theta. Here, this, if you want to calculate this theta, then what we take? x1 y1 means this arc length divided by the radius. Arc length divided by the radius equals to theta. This is equals to x2 y2 upon r plus this small change. That small change is suppose x. Okay. Then therefore x2 y2 equals x1 y1 equals to x2 y2 upon r plus x1 equals to theta. And also x1 y1 upon r equals to theta. x1 y1 equals to theta. Therefore, we can write extension in x1 y1 on bending. Therefore, extension on therefore extension Therefore extension in x1 y1 on bending equals to x2 y2 equal to x2 y2 minus x1 y1. x2 y2 minus x1 y1. This gives us r plus x into theta minus r into theta. On simplifying, we will get r theta plus x theta minus r theta. This r theta will get cancelled and we get x into theta. Means extension in the x1 y1 on bending is equals to x into theta. Now we will calculate the tensile or linear strain. Due to the application of this load, here the strain is produced in the beam and we want to calculate that strain. That strain can be calculated. The definition for the strain equals to extension upon initial length. Tensile strain equal to extension upon original length. Upon original length or initial length. Original length or initial length. This can be written as the extension is just we have calculated it as x into theta upon the original length of this beam is x1 y1. That is the length when the load is not applied to the beam. Okay, this is the tensile strain x theta upon x1 y1. This can be written as x theta upon r theta. This can be written as x theta upon r theta as x1 y1 from this figure. x1 y1 equals to r into this theta. Therefore, here we put the value of r into theta. This value from this equation, this theta get cancelled and we get the x by r as a tensile strain. This then we will calculate then tensile stress. Now we will calculate tensile stress. Stress can be calculated. It is the tensile strain. Stress is equals to force applied on a small cross sectional area. That is F by A. Here this load is applied, means here this force is applied on this cross sectional area. Due to that is the tensile stress produced into the beam. Therefore, F is equal to, it is equals to F upon area of this cross sectional part is considered as the A, delta A, as it is a very small part. Therefore, we consider it as a delta A. Now we will calculate the Young's modulus of the material. Therefore, Young's modulus, if Y is the Young's modulus of the material, if Y is the Young's modulus of the material, then we can write y equals to, then we have y equals to, y is the Young's modulus of what? Of this material. It is equals to tensile stress upon tensile strain. Tensile stress upon tensile strain. Now we have calculated both this tensile stress and tensile strain. Therefore, we will put the values of this tensile strain and stress in this equation. Now, right here, therefore, tensile stress equals to y equals to this tensile stress is given by F upon delta A divided by tensile strain. It is nothing but x by r. On simplification, we will get F into r divided by delta Ax. X into delta A. X into delta A. Therefore, I can write this equation for force equal X delta A upon R into Y. R into Y. This can be written as F equals to Y into X delta A upon R X modulus into X delta A upon R. X by R. This can be written as F equals to X equals to Y into delta A into X by R into X by R. This is the restoring force acting on the area of the filament acting on the filament. Therefore, moment of the force about the axis is given by moment of force about the axis. Moment of force about the axis moment of force about the axis is given by is equals to F into X. Due to this load, there produces a moment of force, and that is given by F into X. Now, putting the values of F, then we get moment of force equals to F is Y into delta A X by R into X. Therefore, this can be written as Y into delta A X square by R into X square by R. This is the moment, bending moment. With this formula, we can calculate the moment of force or bending moment applied due to this load. Now we want for a single layer. This is the moment of force for a single layer, and we have considered that this beam is made up of a number of layers. That layers, the EF is the neutral layer, and the layers below this neutral layer are called the or that that is the layers below this neutral layer, and there are some layers above this neutral layer. Now we want to calculate the moment of force for all layers. That can be calculated as moment of force m equals to the summation of moment of force for all these layers. That can be written as moment of force can be written as y summation of y into delta A x square by r. X square by r. From this we can write this as moment of force equals to y by r summation of delta A into x square. Delta A into x square. The quantity, this quantity here in this equation, this quantity is called the inertia, geometrical moment of inertia. This quantity, that is summation of delta A x square, is called the geometrical moment of inertia of a material, and this is given by the summation of delta A x square equals to I into G. Therefore, this equation I can write here like this. This is the moment of force equals to y by r into Ig. Y by r into Ig. This formula for bending moment of the beam, and this is the formula for bending moment of the beam. So, with the help of this formula, we can calculate the bending moment of the beam. I will stop here. In the next period, we will see the curvature of the beam.